Okay, so on this one, the Earth is being pulled towards the sun, okay, like so. And the moon is pulling the Earth this way, okay? But I can't even draw how small the moon's force is on the Earth compared to the sun's and have it be visible. So I have to exaggerate that it is actually that big, right? It would be like a dot, okay, compared to the force of gravity the sun exerts on the Earth. Okay, so if this is the Earth over here, this is the force of gravity between the sun and the Earth. This is the force of gravity between the moon and the Earth. Okay, and we are looking at the Earth having a net force directed that way, because I have to draw those forces tail to head. Okay. Does that make sense? All right. I'll give you another couple minutes in case that diagram helps you get to a solution. The force of gravity, we have to calculate the force of gravity between the sun and the Earth. Okay, so FGSE, okay, is going to be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 1.99 times 10 to the 30, so the mass of the sun and mass of the Earth, and then divided by 1.50 times 10 to the 11, okay, squared. Okay, because that's the radius. Comes out to about 3.53 times 10 to the 22 or something like that. Okay. Bracket. Okay, 1.99, 30, okay, divided by 1.5, 11. Squared. Okay, so 3.527. So we've got, there's the force of gravity between the sun and the Earth. I got to do the same thing for the moon and the Earth. Comes out to like 1.98 times 10 to the 20 or something like that. Okay, I'm just going to say that for now just to save time. 1.98 times 10 to the 22. Okay, so if I've got those two sides of the triangle, I need to find F net. It's the hypotenuse. So I take those two numbers and use Pythagorean theorem. Okay, so square root of that number squared plus 1.98, 1.98 E20, okay, squared, right? There's my net force, 3.53, barely changed it, right? It changed this 8 from a 7, right? Does the moon make very much difference here? Like virtually none at all, right? That's why the angle is going to end up being so small, a fraction of a degree. Okay, so there's my net force. Now if I wanted to calculate what the angle was, I would go second tan of opposite. That would be the 1.98 E20, okay, divided by the adjacent side, which would be the this number. Right, and I get 0.3 degrees, okay, away from straight to the sun. Okay, so do we have to worry about the moon pulling the Earth out of its orbit? We don't. Okay, we have to worry about very few things pulling the Earth out of its orbit, thankfully, because that would end badly. Right. Something pretty big would have to come by, and come by pretty close, okay, for it to have any noticeable effect on the Earth's trajectory. Now, that said, we saw those videos yesterday where we saw that the force of gravity between the moon and the Earth does cause some strange things to happen for the Earth. The precession, okay, the tides, all of that kind of stuff, that bulge that goes up and slowing the Earth down and all of that stuff, okay, all still true for sure. Okay. All right. Now, where's the one I want? That's the one I want. Okay, similar, but easier because it doesn't involve any trig. Okay, I'd like you guys to try this one, and then I'm going to make up another one that's going to be a little bit more involved. Okay, so Give this one a try. The answer is up there. So we're trying to find the net gravitational force on B. How many gravitational forces are acting on B? 2. The force between A and B and the force between B and C. Right? So I just have to calculate the two of those. So the force of gravity between A and B is going to be 6.67 times 10 to the minus 11 times 10 times 10, because they're both 10 kilogram masses. And they are both half a meter apart. Okay, so if I do that, that should give me the force of gravity, okay, between A and B. All right, so 2.67 times 10 to the minus 8 newtons of attractive force between the two of them. Now I have to do the same thing here. Okay, force of gravity will be 6.67 times 10 to the minus 11 times 10 times 150, or sorry, times 15, not 150, times 15, okay, divided by the same radius, 0.5 squared. Okay, so 6.67 e negative 11, all right, times 10 times 15, bracket, divided by 0.5 squared, all right, gives me 4.002 times 10 to the 8. Negative 8, sorry, newtons. Okay, what do I do with those two numbers? Subtract them. Okay, if I'm trying to find the net force on B, B's free body diagram looks like this. Force of gravity between B and C. Force of gravity between A and B. A and B is a smaller force because we're dealing with smaller masses the same distance apart. All right, so all I have to do is subtract those two numbers, and I get this number, the net gravitational force, except what is that number missing?
Direction.
Right. Towards C. That's it. That's all you have to do, towards C. Okay? So if I'd have given you that question in Unit 2, where I said there's this mass and it's being pushed this way with this much force and this way by this much force, you wouldn't have batted an eyelash at it. Okay? You would have gone, Mr. Coderre gave us such an easy question. It's two forces and I just have to subtract them to find the net force. Boy, that's easy. But as soon as I throw a little monkey wrench into the works, okay, by making me do gravity stuff, okay, we forget the easy stuff. Okay? That net force is the vector sum of all forces. Okay? It's shocking, but that's what happens, right? Is we forget the stuff that was a unit ago, okay, when it still applies. All right, now I'm going to give you a question that involves similar to this, 4 masses. Okay? It might be a preview of something, you know, that you might get later. I don't know, like tomorrow. Okay. All right, what is the net force on the 500 kilogram mass? This one will take you a while. Okay. Could be. Okay. Makes that 4 and 4. What's that do? Well, but I made those two masses the same and the same distance, are those two forces the same? Yeah, which means that when you make a triangle with those two, it's make a 45 degree angle with the other one. You're missing a force. You got this force and this force, they're the same. This force needs to go there. I know, but you don't have it drawn in the right place. It needs to go there. Stay out your head. Good. Yep, yep. Oh, shoot, I've been recording all this blank space. Okay, well, that's nice. All right, just gonna draw a free body, or a vector diagram here. How many forces are acting on the 500 kilogram mass? 3, okay? So you've got the force of gravity here, and the force of gravity between these two, right? And here's the good news, Codere was at least somewhat sympathetic to you, and this force here and this force here are what? They're equal, okay? So it saves you a little bit of calculating, right? And then there's this force here as well, all right? Here's the most common mistake people would make on a question like this. How far is it between those two masses? Is it 1 meter? You'd be surprised how often people put that in. Okay, it's further diagonally across the square than it is from one side to another. Okay, so it's 1.414, I believe. Okay, meters. Okay, in that direction there. So here's what we've got. Here's the mass. Whoa, that didn't work out very well. Here's the mass we're dealing with. Okay, it's being pulled that way, and that way. This force is probably bigger. Probably. Okay, it may or may not be. If those are my 3 forces, that means that from a vector perspective, when I draw them tail to head, they would look like that. Since the two that are perpendicular are also equal, they make a triangle where the angle would be what angle? 45 degrees. Is that also the direction that the 2,000 kilogram mass is going to pull the 500 kilogram mass? Okay, so think about what you got to do in terms of vectors here now. I'll give you a couple more minutes and then I'll walk through the rest of it. And all we have to do is calculate the force of gravities here. We only have to calculate 2 out of the 3 because 2 of them are the same. Okay, so we'll have 6.67 times 10 to the minus 11 times 500 times 1500 divided by 1 squared. So you don't have to worry about that part. Okay, so 6.67 e negative 11, right, times 500 times 1500. Okay, there's our force of gravity between those masses. Okay, and then we also have to do the same thing for the 2,000 kilogram mass. So 6.67 e negative 11 times 500 times 2,000. Okay, so that would be my force of gravity. Oh, sorry, and then I got to divide that by 1.414 squared. Okay, so now I've got the forces that are acting, okay, and now I can put numbers on them. So I'd have, this would be the 5.00 times 10 to the minus 5, and this would be the 3.336 okay, times 10 to the minus 5. Okay, so all I have to do is actually find the hypotenuse of this right angle triangle where the sides are equal, and then add those two numbers together, and I've got my net force, because they both point 45 degrees below the horizontal, or towards the 2,000 kilogram mass. Okay, everyone kind of follow what I did there? Okay, so if I take this number, okay, which is the force of gravity here, okay, so if I take that, and okay, and it didn't give me a bracket, of course. Okay, boy, this is taking a lot longer than it should. All right, plus that same number in brackets. Oh, and that's got to be squared, so I got to go back and square that too. Okay, bracket squared. Okay, so there's my net force, or this side here, 7.07, okay, times 10 to the minus 5. If I take that and I add on this force here, because they're collinear, they go along the same line, there's my net force. 1.0, actually we have 3 significant digits, so no, we only have 1 significant digit here. 1 is our answer. 1 times 10 to the minus 4 newtons towards the 2,000 kilogram mass, or 45 degrees below the horizontal, or something like that. Okay? Now, is one like that, like, reasonable? It's totally reasonable. You only really had to do 3 calculations there. Okay? You had to do a Pythagorean theorem calculation, and you had to do 2 gravity calculations. It seems like it should be a lot more than that, but it really isn't. Okay? It just asks us to remember something from Unit 1 and 2 about vector addition and net force. Okay? Would I give you one like that on a unit exam? No. Okay? It takes too long. I can ask it in a more simple way. But would I ask you one about net gravitational force? Absolutely. Okay, that Earth, Moon, and Sun thing, or the 3 masses right in a row thing, totally. Those would be game for a unit exam for sure. Okay? All right, questions on how that works? Okay. Okay, I'm going to make up a satellite question here I want you guys to try. But I'm going to type it because my writing is so bad. I don't want quotation marks, I want apostrophe. Okay, give that one a try. It's a satellite question. How does it start? FC equals FG. Okay, when we put in those formulas, that's mv squared over r equals big G times the mass of the Earth times the mass of the satellite over r squared. I don't have v. I have period instead. So what do I have to do with this? substitute. I've got to put in the formula for V into this formula. Okay, so I'm going to take this out of here, right? I'm going to get rid of that mass of the satellite because it's going to cancel anyway. 4 pi squared times r squared over t squared. That r and that squared cancel each other off. And now I can go about finding how far above the surface this thing is. First, I've got to solve for radius. So I'm going to multiply r squared to both sides, and I'm going to end up with r cubed over here. Okay, so that's gone. Then I'm going to multiply both sides by t squared. It's gone. Then I'm going to divide both sides by 4 pi squared. It's gone. And then I'm going to take the cube root of that to get r. All right, so that's going to be the cube root of 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 10.4 hours in seconds, which is 37,440. That's not cheap. That's pay attention to details. I would do that on a test in a heartbeat. Okay? This just says, I realize I'm working with force, and the units for force are newtons, and the fundamental units of newtons are kilogram meters per second squared. Okay. Squared, okay, divided by 4 pi squared. See, I only have to do one thing, right? You guys, this is why we do so many examples. Because I only have to do one thing to mess you up. And I should have to do at least 4 things to mess you up. Probably. Okay? So, when I do that, that's going to give me the radius, the orbital radius, which is not the final answer. Okay? So, when we're punching that in, we'll have the cube root. So, math 4. Okay? Bracket, bracket, bracket. 6.67 e negative 11. 5.98 e 24. Okay, 37,440 squared, bracket, bracket, divided by, brackets, 4 pi squared, bracket, bracket. Okay, so there's the overall orbital radius center to center. What do I have to do with that number? Subtract Earth's radius. Which leaves me with 1.78 times 10 to the 7 meters above the Earth's surface. Orbital period needs to be in seconds. You suppose I might try a stunt like that tomorrow? Yep. On a quiz? Or an assignment? Since you're doing both tomorrow, maybe I give it to you in minutes or something instead. Okay? You have to remember you need it in seconds.